This section gives the overview of the whole idea. Every adaptive thing an organism does descends a single scalar. Hold your sensory stream near the observations that keep you intact. Minimize surprise. The chapter's wager sets the neat against the scruffy. The scruffy position is a catalog of dedicated mechanisms, one gadget per task. The neat wager is that the heterogeneous zoo of perception, action, planning, and learning is one imperative seen from different angles, derivable top-down from first principles. Surprise itself is intractable, so the organism minimizes a computable proxy called free energy. Perception bends belief toward the world. Action bends the world toward belief. It is the same descent run in two directions. That one move is what the rest of the book unpacks. To predict the adjacent cases, anything purposive a creature does is this gradient. Read at another timescale. This section explains the single imperative from which everything in the chapter follows. The chapter's wager is the neat's wager. Rather than a separate theory per faculty, one for perception, one for action, one for planning, one for learning, you derive all of them from a single quantity. A creature must minimize the surprise of its own sensations, or rather, its tractable proxy, free energy. This is behavior from first proxy. The primitive to carry forward is a symmetry. Perception and action are one operation seen from two sides. Change your beliefs to fit the world, or change the world to fit your beliefs. Both lower the same free energy. Learning is that move again, only slower. Hold that symmetry, and every later chapter is its unfolding. This section installs the wager the whole book rests on. One question generates everything that follows. How does a living thing stay itself while trading actions and observations with a world that never holds still? The wager is normative. Fix persistence as the sole invariant. Begin from that first principle alone and let cognition and biology fall out as consequences rather than posits. Behavior stops being a catalog of mechanisms to enumerate. It becomes what the imperative to persist forces on anything coupled to its environment through an action, persist forces on anything coupled to its environment through an action Kerala. The chapter's job is to install that inversion. The question is no longer what the brain happens to do. The question is what any enduring system must do. Everything downstream, perception, action, planning, is derivation from the one constraint. This section explains how living organisms persist and act adaptively. An organism does not sit in its environment. It forms a loop with it. Every action reshapes what it will next sense, and every sensation reshapes the next action. To persist is to keep that loop inside the narrow band of observations a body can survive. For a fish, that band is water. The recursion is both the difficulty and the only lever. Each move conditions the next, so viable trajectories are vast, yet nearly all of them are useless. Adaptive control is the selection of the rare, useful ones. It is the same steering problem whether it is solved rigidly, like a bacterium climbing a gradient, or flexibly, like a human planning distal goals. One question runs across every time scale, from evolution to attention. The whole book is its answer. This section names a single wager, one imperative, and everything downstream follows from it. Faced with the sheer heterogeneity of brain and mind, you can take one of two stances. You can be a scruffy working bottom-up, building one dedicated theory per phenomenon, a proliferation without end. Or you can be a neat working top-down, deriving as much as possible from first principles. Active inference is the neat bet pushed to its limit. The diversity is only apparent, and a single normative principle generates perception, attention, action, and adaptation alike. The section itself proves nothing. It stakes the claim the rest of the book must cash. What you should carry is the framing that subsumes the most. If it holds, that is the one the whole argument rests on. This section explains how the book is organized. The book has 2 parts, and the theme between them is theory versus practice. Part 1 asks what active inference is, its conceptual and formal constructs, and it is meant to stand self-contained. Part 2 asks how to use it, working through computational models for perception, attention, memory, and planning. The split gives each reader a natural stopping point. The reader who wants to understand can stop after Part 1. The reader who wants to build reads on. The quiet elegance is that the book's own division mirrors its subject. First the generative model, then action upon it. This is an understand, then deploy arc that recapitulates the very perceive. Then act. Everything past this section is a map you can already predict. The theory chapters assemble the machine, and the practice chapters turn the crank. This section explains active inference in theory, the single imperative that Part 1 unfolds. A living thing persists only by keeping its sensations inside the narrow band that preserves its integrity. A fish, wet, casts that imperative as a quantity called surprise, the gap between observed and preferred sensations, and every faculty becomes one move. Minimize it. But surprise cannot be touched directly, so the agent minimizes a computable proxy, variational free energy. This hands it 2 symmetric levers on the same quantity. It can change its mind to fit the world, which is perception, or it can change the world to fit its mind, which is action. The active part is that second lever. Passivity cannot minimize surprise. Part 1's whole arc is this single imperative unfolded twice. Once from existence downward, once from the Bayesian brain upward, both meeting at the same solution. This section explains why Part 2 of the book exists and what it hands you. Part 2 exists to convert a principle into a procedure. Where Part 1 argues that one imperative, free energy minimization, governs perception, action, and learning alike, Part 2 hands the recipe in Chapter 6, fix the system of interest, choose the generative model form, name the variables. Everything after is that recipe instanced. Discrete time, partially observable. Markov decision processes for foraging choice in Chapter 7. Continuous time. Stochastic models for movement and predictive coding in Chapter 8. Hybrids for saccades. Here is the compression. A normative framework is a factory, one generator emitting model after model for phenomena that each own a separate chapter in any psychology manual. The specific models are disposable. The recipe that makes them is the transferable primitive. You master it by rerunning it, not by memorizing its outputs. This section summarizes the wager. The chapter plants one imperative and the whole zoo of adaptive behavior falls out of it. Every organism, from bacterium to human, is doing a single thing, minimizing surprise. Surprise is the gap between the observations it gets and the observations its continued existence requires. Surprise itself is intractable, so the organism minimizes a tractable proxy called free energy. The move is the neat's bet against the scruffies. It refuses a separate theory for each faculty. Perception, action, planning, and learning are all derived as one quantity being lowered. and this minimizing is active. You cannot lower surprise by watching. You act to make the world match your model. The rest of the book is just two roads, a high road and a low road, into the same scalar. This section explains the chapter's central claim that a single scalar quantity, once minimized, generates the whole agent. That is the thesis. Perception, action, and planning are three ways of lowering one quantity, the variational free energy, which is a tractable bound on surprise. What look like three separate faculties are the same minimization running in three directions. The low road earns this by extension rather than by deduction. It starts from Helmholtz's idea of perception as unconscious inference. It then notices that a generative model already implies a discrepancy between what is predicted and what is sensed. That discrepancy can be shrunk in two ways: change the belief, which is perception, or change the belief, which is perception. Planning is the same move, aimed at the future, scored by expected free energy. The whole apparatus is the direction of fit trick, applied recursively. The high road in Chapter 3 reaches this identical endpoint from self-organization alone. This section explains how Chapter 2 builds toward active inference. Start with the core. Move. A model predicts, the senses report, and the two disagree. The work of the system is to fix that discrepancy, and when it does, one scalar quantity falls. There are two ways to close the gap. You can change the belief to fit the world, which is perception, or you can change the world to fit the belief, which is action. The chapter calls its route the low road, and its central claim is that perception and action are a single objective rather than two. Both minimize one quantity, variational free energy, which is a tractable upper bound on surprise. Planning is the same move cast forward in time. You score each policy by its expected free energy. This is the important turn because it dissolves the old split between exploring and exploiting into a single currency, measured in nats. The chapter's place in the larger arc is accretive. It reaches active inference step by step, starting from the Bayesian brain. This sets up Chapter 3, whose high road can then rederive the identical endpoint from self-organization alone. This section introduces the single idea the whole chapter turns on. Perception was already an inference. The brain never sees the world. It infers hidden causes from sensory evidence by Bayes' rule, what Helmholtz called unconscious inference, and what later became the Bayesian brain. The chapter's move is a single generalization. Take that one operation and apply it to everything. Action, planning, and learning stop being separate faculties and become the same inferential problem, differing only in what is inferred. The second move rescues the first from impossibility. Exact. Bayesian updating is intractable for any real generative model, so it is replaced by a variational approximation, a bound you can actually descend. One rule, universalized, then made computable. Everything downstream, the free energy functional and the agent, is this pair of moves specialized. This section explains why perception is a form of inference. A brain sees nothing directly. It runs its model of the world backward. The forward arrow is causal. A hidden state generates sensation, the probability of the sensation given the cause. Perception is the inversion of that arrow. Given the jump, which cause? The apple or the frog? That inversion is just Bayes' rule. The prior times the likelihood renormalized into a posterior, The apple frog toy in Figure 2.1 is the whole thesis in miniature. A 0.9 apple prior flips to a 0.9 frog once jumping is seen, because the likelihood overwhelms the prior. Here is the primitive to carry. Perception is the posterior of a generative model, not the transduction of a stimulus. It works inside out, not outside in. Every later mechanism in the book is this one inversion scaled up. This section explains what optimality means when applied to a living inference system. Optimality here is a claim an organism makes about itself, never about the world. Bayesian perception counts as optimal only against an internal cost, variational free energy, so the word carries no promise of correspondence to reality. Two wedges pry the model apart from the truth. First, bounded creatures can only approximate exact inference. Second, each organism reasons from its own generative model, whose hidden states, written X, need not even inhabit the same space as the world's true states, written X star. The illusion is the tell. A simpler model can explain a sensation better than the process that actually engineered it. So optimal inference means self-consistent under a chosen loss, forever contingent on the model and its finite resources. Accuracy against the world is neither guaranteed nor demanded. This part explains action as inference, the idea that a generative model can reduce its own surprise by moving either of two things. A generative model scores its own surprise against sensory data, and that surprise is a function of two arguments, not one. Ordinary Bayesian inference minimizes it by moving only the first argument, adjusts beliefs to fit the observations. The fundamental advance is noticing that the second argument is also yours to move. An organism that can act changes how the data are generated. It samples the world so that the incoming observations are the ones its model already predicts. Perception fits the model to the world. Action fits the world to the model. One objective, minimized from both sides. The apple that jumps is surprising. Reach out, and you can arrange to only ever meet apples. Two levers, a single quantity between them. This section explains how perception and action reduce to a single operation. Perception and action are one operation seen from two ends. Both drive a single quantity to zero, the gap between what the model predicts and what the senses report. The only freedom is the direction of fit. You either revise the belief to match the world, or revise the world to match the belief. Which one fires is set by confidence. A loosely held guess, apple, or is it a frog yields, and that yielding is perception? A belief that underwrites survival, like core temperature, refuses to yield, so instead you open the window, and that is action. The move that lets discover biology is that preferences are folded into the prior. So a fish expects being in water, and staying alive becomes just another way of staying unsurprised. This section explains how minimizing variational free energy substitutes a tractable bound for an impossible computation. Exact Bayesian inference is intractable. The posterior, P of x given y, and the evidence, P of y, resist computation, so surprise cannot be minimized directly. The move is to replace both with computable stand-ins, an approximate posterior Q, and a variational free energy, F, that upper bounds surprise. Then you minimize the bound instead of the target. Because F is greater than or equal to surprise, dragging F down drags surprise with it, and the two meet exactly when Q matches the true posterior. This is the elbow move. Replace an intractable objective with a tractable bound, and descend. Its yield is that perception and action become one optimization. Perception tightens the bound by changing beliefs, and action tightens it by changing what is observed. Only sees past and present, which is why planning will need expected free energy. This section explains expected free energy and how planning becomes a form of inference. Start from one functional run in two temporal directions. Perception scores how well the model fits what already happened, and that score is called variational free energy. Aim the same score forward at imagined outcomes, and it ranks actions instead. That forward-aimed version is expected free energy, the fit between a policy's predicted observations and the observations you prefer. Planning then becomes inference. You infer the policy you are about to enact, soft-maxing negative expected free energy into a belief over policies. The quiet economy is that this one quantity splits by itself into two parts: pragmatic value, which is reaching preferred outcomes, and epistemic value, which is resolving uncertainty. Curiosity falls out of scoring futures, the same way you already score the past. It is the frog or apple what if simulation. Run before you jump. This section explains what expected free energy is, and why one quantity absorbs the whole of decision-making. Score every policy by the free energy you expect it to yield, and one scalar splits through a single algebraic decomposition into two pieces: the value of reaching preferred outcomes and the value of information gained. Both are measured in the same units, nats. That shared unit is the entire move. Because the two live in one currency, exploration and exploitation stop being rival imperatives and become two terms of one sum. Minimizing expected free energy prices them against each other automatically, dissolving the classic explore-exploit dilemma. The espresso seeker, who must read the calendar before he can pick the right cafe, shows why both terms. And every classical decision scheme falls out by deleting one term: expected utility, KL control, intrinsic motivation, infomax. One functional subsumes the zoo. This section closes the low road, showing how a single quantity, once minimized, unfolds into the entire architecture. One scalar, minimized, generates the whole architecture. Variational free energy scores how well a model fits the world. Its expected counterpart scores policies by the futures they would bring. The two are nested loops: perception, the outer loop, planning the inner loop, both driven by the same descent. The low road is this bottom-up assembly. Unconscious inference leads to the Bayesian brain, which leads to perception. Action duality, which leads to planning. As inference, each step is forced by the last, and the chain terminates here. Here is the move that pays. An agent's priors are its identity. Preferred states just are expected states, and expected states are the organism's survival conditions. So fulfilling a prediction and staying alive become one act. The high road, taken up in Chapter 3, reaches this same endpoint from the top down, starting from existence itself. This section summarizes how the free energy principle collapses into a single idea. Collapse the Bayesian prior into a survival condition, and the whole theory falls out. A creature carries a generative model whose priors encode not just what it expects, but what it prefers, its niche-specific viable states. Then predicting yourself accurately and staying alive become one operation: minimize surprise. The low road reaches this bottom up. It begins with Helmholtz's perception. As inference, extended so that action too is inference. You act to make sensations match the model, rather than only updating the model to match sensations. Both roads minimize a single quantity. Variational free energy, a tractable upper bound on surprise, approached from complementary sides. The move that carries the chapter is this: an agent's identity is isomorphic with its priors. This section explains the high road to active inference, the argument that turns free energy from a convenience into a consequence of merely existing. To stay a thing is to keep visiting the same small set of states. A fish stays wet, a body holds 37 degrees. Chapter 2 posited free energy as an inference convenience. The high road inverts the arrow. Begin from the physical imperative of persistence, and free energy minimization falls out as its tractable solution. Here is the pivot. Draw a Markov blanket, a statistical boundary, and existence becomes self-evidencing. Internal states come to model the external world, and merely by persisting the organism maximizes evidence for that model. Surprise, minimization, and survival are one and the same. Across the blanket, the two collapse to a single equation. What separates a thermostat from you is only the shape of the attractor. This section turns the derivation around. Chapter 2 assumed inference and got free energy out of it. The high road assumes only that a thing persists and gets inference back as a consequence. Start from the primitive. To exist is to keep occupying a narrow band of characteristic states. Water for a fish, 37 degrees Celsius for you, while the environment's fluctuations push everywhere else. A Markov blanket makes the thing separable from the rest, and the blanket's persistence just is holding sensory states inside their probable range, which is to say, minimizing surprise. So being an organism and gathering evidence for a model of oneself are one fact seen twice. This is self-evidencing. Existence is the premise. Bayesian inference falls out as a consequence rather than being posited. This part explains how the chapter reaches free energy from the opposite direction. Two roads reach the same object, and this chapter walks the second. The first road built free energy as a computational trick for approximate Bayesian inference. This one inverts the arrow. It begins from the physical imperative that anything which persists must hold itself in a narrow band of characteristic states. A fish in water, a body near 30 self in a narrow band of characteristic states. A surprise becomes the technical name for straying outside that band. Free energy minimization then arrives, not as a method someone chose, but as the only tractable proxy for staying alive. The move that binds the two roads is the equivalence the chapter promises. Minimizing free energy is maximizing the evidence for your own model of the world. To persist is to be self-evidencing. This section explains the Markov blanket, the statistical boundary that makes a thing a separate object from its world. A thing is separate from its world exactly when a set of variables, the blanket B, screens the two apart. Given B, the internal states mu and the external states x carry no further information about each other. Formally, the probability of mu and x given B factorizes. It equals the probability of mu given B times the probability of mu. The edge of a creature is therefore a factorization, statistical rather than spatial. That blanket resolves into sensory states, the world writing to the system, and active states, the system writing to the world. So the definition is already the action-perception cycle. Internal reaches external only vicariously, through action, and external reaches internal only through sensation. This is what lets a system be a well-posed object at all. Every downstream claim about self-evidencing rides on the blanket holding. This section explains why staying a bounded thing is the same act as minimizing surprise. To stay a bounded thing is to keep sensing what you expect. A system with a Markov blanket persists only while its sensory states stay inside the narrow set its own model calls probable. Drift outside and the boundary dissolves, so you are no longer that system. Minimizing surprise then describes the very shape of anything that lasts, rather than a goal life chooses to pursue. Surprise is the negative log evidence for your model, so to minimize it is to gather evidence for yourself. That is self-evidencing. Existence and inference become one tautology, read from both ends. The states you occupy fix what you expect, and occupying them proves the model that expects them. This section explains why staying alive takes the exact mathematical form of least action. Persistence is a variational principle. Anything that keeps its form, a Markov blanket whose boundary state distribution stays fixed over time, must, on average, correct every fluctuation that pushes it toward improbable states. Read improbability as energy, a negative log probability, and that correction is descent of a Hamiltonian. The system rolls downhill on a surprise landscape, the way a bowl settles into a basin. See Figure 3.3. Staying alive then takes the exact form of least action. The object physics extracts from mechanics, now applied to a boundaried thing. The generative move is to posit an invariant, not a purpose, and least. Action behavior falls out. The thermostat single basin is the trivial attractor. Richer attractors give richer life. This section is the dictionary that translates between 4 vocabularies. James made a wager that Bayesian inference, information theory, and statistical physics are one object seen from 3 sides. Here, a 4th face gets grafted on: cognition. The dictionary reads as a chain of identities. Minimizing variational free energy is the same act as maximizing model evidence, which is the same act as self-evidencing. Minimizing expected free energy is the same act as Hamilton's principle of least act as Hamilton's principle of least action, which is the same act as planning. Resting at a non-equilibrium steady state is the same act as approximate Bayesian inference, which is the same act. The force of Table 3.1 is that these are translations of the same equations rather than analogies between neighbors. There is one surprise. Minimizing dynamics read in 4 registers, so any term you meet has 3 synonyms living elsewhere. The author guards a single boundary in box 3.2. The equations are borrowed intact, but they rebound onto an agent's belief state rather than its particles, and onto open systems far from thermal equilibrium. This part explains how 3 quantities in the free energy framework collapse into a single gradient you can descend. Model evidence is how well a model predicts its data. It is intractable, and its negative logarithm is called surprise. Variational free energy is a quantity you can actually compute, and it sits always above surprise. The gap between them is exactly the callback. Leibler divergence between your approximate belief, Q of x, and the true possimate belief, Q of x, and the true posterior. So, minimizing free energy squeezes that gap shut and drives surprise down without ever evaluating the impossible integral. Here is the generative move. When a quantity you want is uncomputable, find a tractable upper bound whose slack is a divergence, then descend. Perception is nothing but closing that slack. A system minimizing free energy is, silently, one maximizing the evidence for its own model. This section explains how a preference over outcomes turns into a probability over whole trajectories. Preference becomes probability once you score a whole path rather than a destination. Active inference sets a policy's log probability in proportion to its expected free energy, so the most likely trajectory is the one that minimizes it. Ticks. Action selection then collapses into inference. The agent reads off which path it most probably follows. This is Hamilton's principle of least action, wearing a Bayesian coat. Physics scores a path by an integral of an energy, and the realized path extremizes that action. Here, the energy is expected free energy, and the path is a policy. One generative move reused everywhere. Turn a functional of paths into a distribution over paths. Then let its extremum be the trajectory that actually happens. This section explains how active inference folds value into belief, so that purpose falls out for free. Where Bellman assigns each state a learned reward, value, and behavior climbs toward high value, active inference encodes preference as prior belief. The agent simply believes it will realize what it prefers. Acting to fulfill those preferences becomes the only trajectory consistent with that belief. Teleology is entailed, not something bolted on afterward. And since these energies are negative log probabilities, the most likely path is the one that minimizes free energy. A living thing obeys Hamilton's principle of least action, drifting the path of least resistance to steady state, exactly as a particle does. Value was never primitive. Belief plus least action generates it. This section explains why a creature is identical to its generative model and how depth of that model climbs the ladder towards sentience. The creature is its generative model. Behavior is nothing but what a steady state distribution over sensory data implies. So to specify a model is to specify what a system finds surprising and therefore what it does. Complexity climbs by what the model can represent. A shallow model infers at one time scale. A hierarchical one nests slow context over fast content. A temporally deep one represents the consequences of its own actions across alternative futures. Those controllable futures are the policies, disambiguated by a prior that favors the lowest expected free energy. Agency needs no extra substance, only counterfactual reach. This is the chapter's move. Cognition's ladder is model depth, and sentience sits where a Markov blanket can imagine what it might do. This section explains how three theories of the living system, once thought incompatible, turn out to be one theory seen from three angles. The three traditions are inactive. Self-organization, where autopoiesis resists dispersion. Cybernetic teleology, where behavior tests and corrects toward a goal. And model-based prediction, where control rests on an internal model. Biologists thought these were irreconcilable. They collapse into a single move. The moment you name the quantity, each one is single move. The moment you name the quantity, each one is secretly minimizing. That quantity is variational, free energy. Each tradition is a projection of its minimization seen from a different angle. Staying in preferred states is low surprise. Closing the gap between preferred and sensed is prediction error. And the good regulator theorem forces any controller to be a model of its world. Self-organization and teleology only looked opposed because no one had the common measure that renders them the same optimization. This section explains how a single parameter grows. the whole ladder of adaptive systems, from virus to planner. That parameter is the temporal depth of the generative model. Every adaptive system is already a self-evidencing agent. It samples sensation to minimize variational free energy, gathering evidence for the model it is. That buys homeostasis, even virulence, yet it lives strictly in the present. Give the model a time axis, and it minimizes expected free energy instead. It carries the prior that it is an agent who will minimize free energy in the future, so it selects among alternative futures rather than only the sensed now. Agency arrives as planning, falling out of a model that learned to represent time. Temporal depth becomes psychological depth. This section summarizes the whole chapter in a single move, so hold on to the one equivalence that drives everything. A thing that persists is a thing that keeps its statistical boundary, its Markov blanket, intact against the environment's fluctuations. Holding a boundary constant just is staying in a narrow set of characteristic states, which just is minimizing the surprise of what you sense. That single equivalence is the chapter's whole engine. To exist, to infer, and to self-evidence are one operation seen from three angles: thermodynamic, Bayesian, cognitive. Surprise itself is intractable, so life minimizes variational free energy, its computable upper bound. Behavior then falls out as Hamilton's principle of least action. The high road earns. Active inference from first principles. The low road did the reverse, positing inference and then finding free energy convenient. This section explains one object and one move. The generative model, a joint distribution over hidden states and observations, is the only thing this chapter posits. Free energy minimization is the only thing it does. Perception, planning, and action stop being three mechanisms and become three arguments to the same gradient descent. Either change beliefs to fit data, or change data to fit beliefs. The two model families built here, the discrete POM-DP and continuous predictive coding, are that identical move under two encodings of time, a sequence of events versus generalized coordinates of motion. What the chapter is for in the book's arc is this collapse. The conceptual sprawl of chapters 2 and 3 becomes a single scalar. You descend, and every later chapter is one instance of the descent. This section shows how a single operation generates the whole apparatus. That operation is gradient descent on variational free energy over a generative model. Everything the earlier chapters gave you conceptually, perception, action, and planning, is this single move. The chapter's real work is to show that the only degree of freedom left is how the model represents time. Categorical events yield the POM-DP with its A, B, C, and D matrices. Continuous flow yields generalized coordinates and predictive coding. The equations force one surprise. There are two free energies here, not a single one. Variational free energy, F, is minimized against data already in hand. Expected free energy, G, selects the data worth gathering. Same functional, opposite direction. Action closes the loop by minimizing F through changing the world, rather than changing the F through changing the world, rather than changing the world, rather than changing the Bellink. This section explains how the chapter turns an informal principle into a working program. Prior chapters told you what active inference is. Here, it becomes a machine you can actually turn. You fix a generative model. You minimize variational free energy, and every faculty, perception, planning, motor control, precipitates as the dynamics of that single minimization, never as separate mechanisms bolted together. The one knob that forks the entire formalism is how time enters the model. Time enters either as a discrete sequence of events, the POM DP, or as continuous flow, the generalized coordinates of motion. One principle, two temporal factorizations. Message passing is what running the minimization looks like from the inside. Predictive coding is simply its continuous time instance. This section explains how Bayesian inference turns into free energy. Exact. Bayes needs the marginal likelihood, an integral over every hidden cause, and that integral is generally intractable. The move that generates free energy is to trade the integral for an optimization. Here is how the trade works. Insert an arbitrary distribution, Q, inside the sum, which changes nothing, since multiplying by Q divided by Q is multiplying by 1. Read the result as an expectation. Then, Jensen's inequality, applied to the concave logarithm, turns the log evidence into a lower bound. That bound is the variational free energy. Driving Q to minimize it does two things at once. It pushes Q toward the true posterior, and it pushes the free energy, F, toward the negative log evidence. Approximate inference becomes gradient descent. The quiet elegance is this. Self-evidencing fixes which divergence to minimize, so Jensen picks the measure uniquely, and the usual choice of metric ambiguity never arises. This section explains what a generative model is at the structural level. A generative model is nothing but a factored joint distribution over hidden causes and their sensory consequences, prior times likelihood. Draw it as a factor graph, where the arrows are the causal claims themselves. Fix that graph, and everything downstream is determined, the free energy and the message passing that minimizes it. The model is the whole commitment. Active inference adds exactly two things to that static picture. First, the graph unrolls in time. Second, how I am acting enters as just another hidden variable. Two canonical shapes then exhaust the chapter. The discrete and categorical case is the POM DP. The continuous case is stochastic differential equations in generalized coordinates. These are the same object under two representations of time. The clinical diagnosis factor graph anchors the static case. Time is the only axis separating the two forms. This section explains how active inference works when time moves in discrete steps. Give an agent 4 tables, a likelihood called A carrying hidden states to outcomes, a policy-dependent transition called B, an initial state prior called D, and a preferred outcome vector called C. Give it one imperative, minimize surprise. Planning then collapses into inference. A policy is just another hidden variable, so its prior is the expected free energy it would incur, and choosing what to do becomes inferring which action sequence a surprise minimizer would take. The generative move is the same variational calculus that explains perception, aimed at the future instead of the past. A single sign flip separates the two. Perception prefers data that confirm current beliefs. Planning prefers data that most change them. Everything downstream is that one substitution run forward in discrete steps. This section explains what a partially observable Markov decision process is at the structural level. A POMDP factors a temporally extended world into a hidden state you never see directly, plus 4 matrices. The state causes the observation through a likelihood, called A. It flows to its successor through a transition, called B, which the policy indexes. Choice enters the world only here, by selecting which B governs the next step. D fixes the world only here, by selecting which B governs the next step. Here is the compression. Observation and action are one joint read taken in opposite directions. Perception inverts A. Planning ranks the B's. The policy never touches the likelihood. It steers the flow alone. Everything the agent knows lives in A, B, and D. Everything it wants lives in C. This part explains how active inference turns a whole decision problem into a single operation. Fix 4 distributions, the likelihood A, the transitions, B, the preference, C, and the initial prior D. Once those are set, the entire decision problem collapses onto one operation, gradient descent on variational free energy, executed as message passing. Perception and planning are not separate faculties. Perception asks which state you are in under this policy. Planning asks which policy to follow, and both are the same crank turned on different variables. States are updated through equation 4.13, policies through equation 4.14, with a softmax reading beliefs off the accumulated gradient. That is the primitive the section hands you. Once the generative model is specified, nothing bespoke remains. A single minimization generates both inference and choice, and the message passing graph doubles as a candidate wiring diagram for cortex, with nodes as populations and edges as synapses. This section explains how active inference behaves when time is continuous. One equation runs in both directions. In continuous time, active inference collapses to predictive coding. The agent carries beliefs about a whole trajectory, position, velocity, acceleration, the generalized coordinates of motion. And it does gradient descent on a single quantity. Precision-weighted prediction error. Perception moves the belief to fit the sensations. Action moves the sensations to fit the belief. That second arm is the surprise. The motor system needs no separate controller, no inference over which action to take. A classical reflex arc simply annihilates prediction error at the periphery, so predicting a movement is already performing. This is the continuous mirror of the discrete POMDP scheme. It is the same free energy minimization, but error cancellation replaces policy selection. This section explains how predictive coding emerges from free energy minimization once you fix the generative model. Predictive coding is what free energy minimization looks like at that point, a Kalman-Bucy filter stripped of its Wiener assumption. The model has 2 equations. The hidden dynamics say x dot equals f of x and v, plus a noise term omega x. The observation says y equals g of x and v, plus a noise term omega y. Both noise terms are Gaussian, and together they give the standard filter. But biological fluctuations are smooth, correlated across time, so a lone state points E. The generative move is to carry the entire trajectory as generalized coordinates of motion, value, velocity, acceleration, and the higher derivatives together, where about 6 suffice. The derivative operator d shifts one coordinate into the next. Apply the Laplace approximation, and free energy collapses to a sum of squared, precision-weighted prediction errors. That algebraic form is the section. Predictive coding is this model's free energy read-off. This section explains how active inference folds motor control back into perception. Motor control collapses into perception the moment you let action minimize the same prediction error. The move is this: send a predicted proprioceptive signal down to the spinal reflex arc, the simplest possible controller, and let the muscle correct the gap between predicted and sensed limb position. The limb moves because it was predicted to move. There is no inverse model, no cost, no value function. Action and inference become one free energy gradient, differing only in whether belief bends to data or data is bent to belief. In Chapter 4, the whole idea compresses to a single line. Active inference is just predictive coding plus reflex arcs. Value and cost dissolve into priors. What you predict at the bottom is what you prefer. This section summarizes the chapter where one scalar quantity does all the work. It recasts intractable Bayesian inference as descending variational free energy, a bound on surprise you can actually compute from a generative model. This chapter is the formal hinge of the book. It turns the earlier conceptual low road and high road into the single quantity every later mechanism minimizes. The generative model comes in two flavors, keyed to what you are inferring. The first is categorical states in discrete time, the POMDP case. The second is continuous states carried in generalized coordinates of motion. Minimizing the free energy over either falls out as local message passing between neuron-like populations, which in the continuous case is predictive coding message, which in the continuous case is predictive coding. Here is the generative move. You can lower the free energy two ways. You can bend beliefs toward the data, or you can act to bend the data toward your beliefs. Perception and action. 1. Descent. This section explains how free energy minimization gets committed to the brain. Free energy minimization is a principle. It says nothing falsifiable until you nail it to a substrate. This chapter performs exactly that commitment. It reads the belief update equations of Chapter 4 as a wiring diagram and asks the brain to match. The move that makes it work is a matching of sparsities. Variational inference is sparse, each variable coupling to few others. Cortex is sparse too, each neuron speaking only across its synapses. So the factor graph is the connectome. From there, prediction errors ascend and predictions descend, and every arrow becomes a measurable prediction. Gamma rhythms go up, alpha and beta go down. Dopamine acts as policy precision. The chapter is the book's hinge, turning from mathematics that must be true to biology that could be wrong. This section explains why a factorization graph and an anatomy graph are the same object read twice. A principle says what a system optimizes. A process theory says what hardware could do the optimizing, and only the second is answerable to a microscope. Chapter 5's move is this. Variational inference already factorizes. Each variable in the generative model couples to only a few others, so belief updates travel as local messages on a sparse graphles to only a few others, so belief ups a shovel as locus. The brain wears the same sparsity. A neuron talks only to its synaptic partners. Equate the two graphs, and free energy minimization stops being a slogan and becomes a wiring diagram. Message. Passing schedules predict cortical microcircuits, neuromodulation, and motor reflexes. The primitive is this. A factorization sparsity is itself a claim about physical connectivity. Same graph. Read once as inference, once as anatomy. This section introduces why demoting a principle to a process theory is what makes it testable. A principle says what must be minimized. It never names the machinery, so it cannot be wrong. The chapter's move is to demote free energy minimization to a process theory, one substrate that implements it, and therefore one that empirical data can refute. The bridge is sparsity. Variational inference factorizes because each variable couples to few others. The brain wires sparsely for the same reason. A neuron listens only to its synaptic partners. Identify the two graphs. Match message, passing edges with synapses, and gradient descent with neuronal firing. Then Bayesian belief. Updating becomes neuroanatomy you can measure at the scalp. The principle constrains everything and predicts nothing. Only the process theory sticks its neck out. This section explains how the cortical wiring diagram and the inference algorithm predict each other. Read the cortical wiring diagram as an algorithm, and the algorithm predicts the wiring. Active inference is belief, update equations form a message. Passing graph, and that graph lands on the 6-layer column. Ascending prediction. Errors leave superficial pyramidal cells. Descending predictions leave deep ones, and error units wait in layer 4. One canonical microcircuit repeats at every rung, because the same inference runs at every level of the hierarchy. The payoff is that anatomy becomes prediction. Computing an error is nonlinear and raises frequency, so ascending traffic should ride gamma and descending traffic should ride alpha or beta, which recordings confirm. The mapping is many to one. Where a descending arrow seems to hit the wrong layer, a dysynaptic detour through inhibitory interneurons resolves it. The circuit is inference made flesh. This part explains what a motor command actually is. A motor command is a prediction of movement. The standard picture says the brain computes muscle activation error and ships them down the spine as instructions. Active inference turns this around. Bet cells in motor cortex predict the proprioceptive consequences of a movement, and the spinal reflex arc consequences of a movement, and the spinal reflex arc contracts the muscle precisely to cancel the resulting prediction error. Movement is error, resolution by changing the world rather than the belief. Action is the dual of perception. It descends the same free energy gradient, only in the opposite direction. This is why layer 4, the error-receiving input layer, is sparse in motor cortex. Proprioceptive errors get discharged by reflex, not by revising the model. To move, predict having moved, then let the body make it true. This section explains how to read the subcortical structures as terms in a single equation. Read every nucleus as a term in one equation. Cortical layer 5 forks. To the spinal cord, it sends proprioceptive predictions. To the striatum, it sends the ingredients of expected free energy, the scalar that scores a policy. So the basal ganglia are the anatomy of planning itself, the machinery that evaluates alternative courses of action rather than a separate motor box. The direct pathway through the D1 receptor and 1 inhibitory synapse disinhibits behavior. The indirect pathway through the D2 receptor with 2 inhibitions and an excitation suppresses it. Together, they compute the posterior over pollices pi readout in the internal globus pallidus. Here is the move to carry forward. Given any structure, ask which term of the free energy message passing its wiring implements. Here, the planning term. This section explains neuromodulation as the brain's precision control on learning. A neuromodulator is a precision knob. The confidence weight. The brain multiplies onto one specific family of prediction errors. Structural connectivity says which regions can talk. Precision says how loudly, and it is the same inverse variance gain that turns a belief update up or down. The generative move is that every distribution in the model carries its own confidence, so each one needs a physical channel to set it. Dopamine sets confidence in which policy. Acetylcholine sets confidence in likelihoods. Noradrenaline sets confidence in transitions. Serotonin sets confidence in preferences. Learning is just the slow version of the same dial. Here is the inversion that does the real work. Dopamine's famous reward prediction error is reread as rising confidence that you are on the right policy, not reward itself. This section explains why the brain runs two kinds of message passing at once, and how a single hierarchy blends them. The brain runs two message passing schemes at once because the world hands it two kinds of variable. Continuous ones live at the sensory motor skin, things like muscle length and luminance contrast. Categorical ones live deeper in, things like which object this is or whose face. A single hierarchy therefore grades from continuous below to discrete above. The periphery must be continuous, since that is where the interface with the world sits. Here is the move that stitches the two together. A discrete hypothesis names the continuous dynamics it entails. So a purposeful movement becomes the composition of discrete trajectories, with basal ganglia policy selection choosing which continuous reflex arc to descend into. The prediction falls out cleanly. The further a neuron sits from a receptor, the more categorical its tuning. A classical receptive field already partitions a continuous state space into little categories. This section draws the line between a principle and its implementation, the distinction the whole chapter turns on. A principle and its implementation are different objects, and the chapter turns on keeping them apart. Free energy minimization says what the brain optimizes. It says nothing about how meat does it. The process theory supplies the missing map. It sends belief update equations onto cortical microcircuits, prediction errors onto ascending gamma, precisions onto neuromodulators, and policy evaluation onto the basal ganglia. What that map buys is falsifiability. The abstract model now predicts evoked potentials, dopamine spikes, and pupil dynamics, quantities a scalp electrode can read. Its worth comes from what it enables, not from being correct. The authors flag it as provisional, replaceable, and openly call it not the final word. It is the smallest structure that turns a principle into a hypothesis, answerable to measurement. This section explains the recipe for designing active inference models. Everything downstream, perception, planning, and neural dynamics falls out of a single fixed operator, descent on free energy. The whole design labor therefore collapses onto specifying the generative model, the axe sharpened before the tree falls, as Chapter 6's Lincoln epigraph has it. That specification reduces to 4 choices. First, where the agent's boundary sits, its Markov blanket. Second, whether inference runs in discrete or continuous time and how deep. Third, which variables and priors are fixed versus learned. Fourth, the external process that generates the sensations. Fix those 4, and behavior is determined. You state the problem, and the solution self-evidences. The method works top-down rather than by emulating the brain. You find the model describing what a system solves, and its dynamics come for free. This part explains where the real work of active inference design lives. The whole labor sits in the specification. Lincoln's axe from Chapter 6 captures it. 4 hours spent sharpening, and then the tree falls almost by itself. The solving is the easy part. Once the specifying is done, active inference design runs top-down. You never emulate a brain piece by piece. Instead, you name the generative model of the problem the agent faces, and behavior, perception, and neural dynamics all fall out as free energy minimization. The chapter compresses this into a 4-step recipe, where each step resolves one design choice rather than a computation. First, you fix which system you are modeling by pinning down its Markov blanket. Then you choose the appropriate form of its generative model. Then you set how its variables and priors are configured. This is the hinge that turns theory into practice. Once the model is written, the solution is already implied. This section introduces the chapter's single primitive. Design nothing about the behavior. Specify only the problem, and the behavior falls out. That inversion is the whole idea. Active inference is top-down and normative. You do not emulate a brain circuit by circuit. You write down the generative model, the object that states what the system is trying to infer. Then, perception, planning, and neural dynamics are all forced as the descent of internal and active states on that model's free energy. The generative model is a complete description. Everything downstream is derivation, not engineering. This is the variational move, recast as cognitive design, fix the functional, and the trajectory is determined. The recipe that follows is just how you choose that one object well. This part explains how to design an active inference model, a recipe in 4 steps. Every active inference model runs the same fixed dynamics, internal and active states descending on a free energy functional. So design work is pure specification. Make 4 choices and the engine follows for free. First, decide where to draw the Markov blanket. What is agent, meaning the generative model? What is world, meaning the generative process? And what is the sensory and active interface between them? Then choose the model's form, discrete or continuous, shallow or hierarchical, temporally deep enough to plan. Then choose its content, the variables and priors split across 2 timescales. Fast inference over states, slow learning over parameters. Last, specify the generative process that actually emits observations, kept distinct from the model. Fix these 4, and behavior is already determined. This section explains the first step of modeling a system under the free energy principle, and why that step is a choice rather than a given. Modeling does not begin with equations, it begins with a cut. Step 1 of the 4-step recipe is to draw the Markov blanket, the sensory and active surface to which internal states touch external ones, and everything downstream inherits from where you place it. The surprise here is that the blanket is not given by the substrate. The same neural tissue is a system inferring the world when you wrap the blanket around the retina and the muscles, and a system inferring the rest of the brain when you wrap it around one neuron. Extend it past the skin, and the calculator joins the internal states. Nesting is free, neuron, brain, organism, community. Choosing the boundary is itself, choosing what infers and what gets inferred. This section explains how you choose the form of a generative model. The choice collapses to positioning the model on 3 orthogonal axes. First, whether its variables are discrete or continuous. Second, whether its structure is flat or hierarchical. Third, whether its horizon is present only or temporally deep. Each axis is a hypothesis about the world's causal grain, not an implementation detail. You pick discrete variables for symbolic transitions between states and continuous variables for rates of change. You add hierarchy when causes evolve at separated timescales. You add temporal depth precisely when the agent must weigh the consequences of plans, rather than merely register what is you. The design space factorizes. You specify a model by committing on each axis independently. Here is the surprise. What look like modeling conveniences are ontological claims. The message passing, and thus the predicted neural dynamics, differ under each choice. This section explains why choosing a discrete or a continuous variable is the modeler's first real commitment. Whether a variable is discrete or continuous is computationally a non-choice. A continuous quantity discretizes, and a discrete one re-expresses itself through continuous parts. Yet the selection is the modeler's first commitment because it encodes a hypothesis about the time course of the process. Discrete variables denote transitions between types at each step, identities, plans, decisions. Continuous ones denote rates of change, position, luminance, muscle length. The type fixes what the cognition is temporally. Its representational convenience is secondary. And the commitment propagates. Each style implies a different message passing, and hence a different neural process theory. Continuous schemes underwrite predictive coding. The two compose. A discrete state, such as object identity, generates continuous outputs, such as luminance. So the real frontier is the hybrid itself, the composition of both, rather than either one alone. This part explains why depth in a generative model is the same thing as a separation of timescales. Depth is separation of timescales. Higher levels evolve slowly and set the context in which the faster lower levels resolve. A shallow model runs everything on one clock. You reach for a hierarchical one exactly when the phenomenon stratifies, phonemes inside words, inside sentences, or the intention of entering the apartment holding still while finding keys and opening the door. Churn beneath it. The generative move is that each level treats the level below as its own sensory stream, a Markov blanket around a timescale. So you can model word processing without simulating phonemes, summarizing the fast layer as observation. Slow context contextualizes fast content, and the near independence of the scales is what buys the computational saving. Predict the rule. Wherever context outlasts content, depth follows. This section explains why planning requires a model with temporal depth. A model either carries the future or it does not, and that one bit is temporal depth. A shallow model scores present observations only. A deep model encodes how each action branches the present into conditional futures. Turn left, turn right, a cognitive map in Tolman's sense. Planning is precisely the operation that needs this. In active inference, you select the policy that minimizes expected free energy, and expected free energy is a functional of future observations. Those cannot be observed by definition. They exist only as generated by a model that knows how actions produce what comes next. So planning reduces to temporal depth. Depth makes the counterfactual future computable, and policy comparison follows. Strip the depth away, and there is no future observation left to score. This part explains how setting up a generative model reduces to just two decisions. The first decision is to name the variables, the hidden states, the observations, and the actions under which your target becomes the common cause of its sensory consequences. Take the jumping frog concept in Figure 6.2. It sits at the center, sensations radiate outward, and inference runs the arrows backward. The second decision is to draw one line, which variables you fix by hand as priors, and which the data updates. That line is almost arbitrary because learning and inference are the same free energy update, split only by time scale. States move fast at the pace of neural dynamics. Parameters move slow at the pace of neural dynamics. You do not emulate a brain piece by piece. You specify the problem as a generative model, and behavior, perception, and neural dynamics all fall out of minimizing free energy. This section explains how a generative model gets set up, starting from the variables that define it. A generative model is a hypothesis about what causes your sensations, written as variables, hidden states, observations, actions, and the probabilities linking them. The hard creative move is choosing those variables. Everything downstream, the A, B, C, and D matrices, is bookkeeping once they are fixed. The jumping frog anchors it. One modal hidden cause fans out into modality-specific percepts, each generating its own sensations, some of them contingent on action, where touch leads to a jump. Perception is just the inversion of this, reading the common cause back from its scattered effects. Here is the generative primitive. To model a mind's grasp of anything, name the smallest set of hidden causes whose forward mapping regenerates the data, then let inference run backward. Design is choosing that skeleton. This section explains which parts of the generative model are fixed and which are learned. Nothing in the machinery distinguishes what is fixed from what is learned. The same Bayesian belief update runs over both, and the only difference is rate. Inference updates beliefs about states. This is fast. A red thing becomes an apple. Learning updates beliefs about parameters. This is slow. Many red apples build a stronger apple. Endow a distribution with priors over its parameters and it becomes learnable. Withhold them and it stays hand-fixed. So learning is a design choice. You simply choose which quantities you let drift slowly. The generative primitive is that a parameter is just a state with a long time constant. This is why inference maps to neuronal dynamics and learning to synaptic plasticity. One algorithm, two clocks. This section explains the final design step, setting up the generative process, the world itself that emits observations. The surprise is that it comes last. You usually assume the world coincides with the agent's model, so you get it nearly for free. Yet, identical structure can hide opposite ownership. The shared A matrix is objective fact for the process and subjective belief for the model, measurement on one side. The good regulator theorem sets the real constraint. An effective agent must be a good model of what it regulates. But how much it resembles the world is a dial you set, never a fixed requirement. You can mirror the world in full, encode only the sensory motor contingencies, or offload the control to the body itself. How much the map must resemble the territory is itself the design choice. This section explains why, once the model is specified, everything else collapses to one procedure. Once the generative model and generative process are written down, the design work is finished. Simulating, visualizing, analyzing, and fitting data collapse to one procedure applied 4 ways: the descent of active and internal states on the free energy functional. The modeler's labor front loads entirely into specification. Execution is a fixed algorithm. The SPM routines run off the shelf. All variation then lives in parameters rather than logic, the temporal depth of planning, selective ablation of expected free energy terms, neuromodulatory gain on priors. That last knob carries the chapter's quiet reach. Push a creature's priors too strong or too weak, and the same machinery yields a psychopathology of inference, a phenotype read straight off a parameter regime. This summary names the single move behind modeling any agent. To model an agent, you choose its generative model. You do not build a copy of its machinery. Behavior, perception, and neural dynamics all descend from one object as free energy minimization over that generative model. Design then collapses to 4 choices. First, where you cut the Markov blanket, what does the inferring and what is inferred? Second, the form of the model, discrete or continuous, shallow or hierarchical, and deep enough in time to plan futures. Third, which variables and priors you write in by hand and which you leave for learning to fill. Fourth, how far the external generative process is allowed to differ from the agent's belief about it. Fix those 4, and the agent is fully determined. Everything that follows is the same descent, run under different settings. The recipe is a coordinate system. It names the axes along which agents vary, rather than handing you a procedure to run. This section explains why active inference in discrete time is one machine viewed from every angle. The abstract free energy imperative of the earlier chapters turns concrete the instant you fix the state space to categorical variables in discrete time. Once you do that, active inference simply is the inversion of a partially observable Markov decision process, with the hidden Markov model as its choice-free degenerate case. Feynman's epigraph names the chapter's job. What I cannot create, I do not understand. A principle earns its keep only when it runs. Perception, decision, information-seeking, learning, and hierarchy are a single belief update watched from 5 starting conditions, with complexity added 1 term at a time. They look like 5 mechanisms, but they are one. The boundary is the state space itself. Discreteness buys innumerable belief. Continuity demands another calculus. This section explains how a single constructive move underlies the whole range of cognitive faculties. The whole zoo of cognition, perception, decision, curiosity, learning, and reading collapses to one constructive move. Write the generative model as 4 objects, the likelihood A, the transitions B, the preferences C, and the priors D. Then invert it by minimizing free energy. Nothing else is added. Perception is that inversion carried out over the amateur musician's notes. The T-maze rat's exploration, followed by exploitation, is the same inversion once a policy variable conditions B. Learning is the same inversion again, aimed 1 level up at the matrices themselves. The chapter's Feynman epigraph is the thesis itself. What I cannot create, I do not understand. A faculty counts as understood exactly when you can specify the model whose inversion generates it. This section opens the chapter with a single thesis, carried by Feynman's epigraph. What I cannot create, I do not understand. Everything before was principle stated abstractly. Here, the single machine actually gets built, variational free energy minimization over a discrete, categorical generative model, the POM-TP. The move that makes the chapter go through is this: perception, decision-making, information-seeking, learning, and hierarchical depth are one mechanism, read at different settings of the same model. You do not bolt on a module for curiosity. You unmask it by parameterizing what was already present. The primitive to carry is this: a theory earns its keep by what falls out of instantiating it, not by what it asserts. Each cognitive capacity is an emergent special case, predictable once you know which knob it turns. This section explains perceptual processing as inference. Perception is your generative model run backward. You hold a model of how the world produces your senses, a hidden Markov model, the simplest, action-free case. Hidden states, the note the musician meant, emit outcomes. The note you hear, through a likelihood A. States chain through time by transitions. B from a prior D. To perceive is to invert D, to recover the hidden cause from the observed outcome. The amateur musician anchor lands the whole move. You hear an off note, and the belief update prefers the probable cause, she slipped, over the improbable one, a rare transition, while keeping a sliver of doubt. Perception is Bayesian inference over what must have generated this observation. This section explains how decision and planning become forms of inference. Promote action to a hidden cause. Once a policy conditions the state transition dynamics, once the extra variable pi sits on the transition matrix B, choosing collapses into the same operation as perceiving. You infer which policy best explains a sequence of sensations you generated yourself. Planning is model comparison. A policy is just an explanatory hypothesis, scored by the expected free energy it incurs. That score splits cleanly into two parts. Epistemic value is the information you stand to gain. Pragmatic value is the preferred outcomes realized. Because both minimize one functional, the exploration and exploitation dilemma never needs arbol. The T-maze rat shows it. It detours to the Q because that observation resolves the context. Reward does not live there. The detour buys information first, and then the rat exploits. Decision reduces to inference. The instant action becomes something to be inferred. This section explains why curiosity is not a drive you add on top of reward seeking, but something that falls out of the same functional. Curiosity comes from the very quantity the agent is already minimizing. Expected free energy splits into two parts. The first is pragmatic value. Make your preferred outcomes likely. The second is an epistemic term, and that epistemic term is exactly the salience of a policy. Salience here is the mutual information between hidden states and the observations the policy would bring. In other words, the uncertainty you expect that policy to resolve. The T-maze rat shows this directly. It visits the Q arm before the baited arm. No reward waits in the Q arm. What waits there is the fact of which arm pays. Because exploration and exploitation are two terms of one quantity, the agent never has to hand balance them. Minimizing surprise and expectation already compels you to sample what you do not yet know. This section explains why learning and perception are the same operation, running at different speeds. Learning is perception with the timescale slider moved. Nothing new is added. Take the parameters, A and B, and promote them from fixed furniture to slow hidden variables carrying Dirichlet priors. A yin-verting the generative model over those parameters is learning, exactly as inverting over states is inference. The two differ only in rate, with the parameters updating once the states have settled. The same information gain term reappears one level up. Salience is to inference what novelty is to learning. Each one is the anticipated belief change from an experiment, now about A rather than S. Exploration then costs nothing extra. Dirichlet counts grow where you have looked. Novelty drains there, and inhibition of return, the avoidance of the already seen, falls straight out of free energy. Minimization. This section explains hierarchical or deep inference, the move that stacks a partially observable Markov decision process on top of itself. Take the same POM-NDP and stack it on itself, but let each higher state persist across an entire trajectory below it. One sentence holds fixed while its words are read one at a time. That single move, a slow variable contextualizing many fast ones, factorizes time itself into nested scales, and it is the whole content of deep inference. The higher level never touches the world. Its predictions descend as empirical priors for the level beneath, while accumulated evidence climbs back up. The reading anchor from Frist, Roche, and colleagues in 2017 shows it. Word evidence sharpens the sentence, and sentence belief sharpens the next word. Same free energy minimization, recursively unstable to arbitrary depth, a world of many timescales. This section summarizes the whole chapter in one idea. One engine gives rise to many faculties. Perceptual inference, planning, the split between exploring and exploiting, learning parameters and learning structure, seeking novelty. Each of these is the same free energy minimization. They differ only in which generative model you feed it. The chapter's move is to hold the inference invariant and vary the model. Put priors over parameters, and learning appears. Nest timescales and deep temporal inference appears. Factorize states, and the separation between what and where appears. The faculty is a property of the model, never of a bespoke algorithm. That is the generative primitive. You do not engineer a new mechanism for each cognitive problem. You specify a generative model and read the behavior of one fixed operation. Every discrete time example in the chapter is a single dial setting of that one machine. This section explains Chapter 8, Active Inference in Continuous Time, where movement is a prediction. The body then makes true. The single move is this. In continuous time, action lives in the generative process rather than the model, so the agent never computes which motor command reaches a goal. That computation, the inverse model, is what every other motor theory builds. Active inference does without it. Instead, the agent predicts the proprioceptive consequences of the limb already being where it should be. Reflex arcs then resolve the resulting error by moving. A command is a prediction whose mismatch is nulled by acting rather than by revising belief. Everything downstream is this one inversion applied. Spring law dynamics, sequential attractors, and sensory attenuation. The attenuation being the license to hold the false belief that I am moving, all follow from it. Control. A self-fulfilling prophecy across the Markov blanket. This section explains how a limb moves when action is treated as inference. A limb moves because you predict where it will be and let reflex arcs null the resulting error. There is no inverse model, no motor command computed backward from goal to muscle. That absence of inversion is the chapter's whole primitive. In continuous time, acting is the error, canceling half of inference, so every behavior reduces to writing a generative model whose predicted trageling half of inference, so every behavior reduces to writing the generative model whose predict fadge. The same primitive scales across the shape of the prediction. Attractors draw a limb to a point. Lotka, Volterra dynamic sequence steps. Lorenz systems generate birdsong. Two agents, each predicting the other's song, synchronize. that synchrony is a collapse onto a shared manifold, and it is primitive theory of mind. Its place in the arc is to give Chapter 7's discrete decisions a continuous body, turning choices into movement and back. This section introduces the continuous time regime of active inference. Continuous time is the same active inference recipe, run on a substrate that flows rather than steps. Where Chapter 7 gave discrete states and discrete choices, here states and sensations vary smoothly. The regime fit to the physical fluctuations hitting receptors and the continuous motion of muscles pushing receptors in a continuous motion of muscles pushing back on the world. The generative primitive to carry forward is this: nothing about free energy minimization changes. Only the state space does, moving from categorical to differential. The chapter's whole payload is one displacement. You swap discrete transitions for a pair of stochastic differential equations, one relating states to sensations, the other governing how states evolve. Everything downstream follows from that single change of arena: motor control as inference, dynamical systems, generalized synchrony, and the reconciliation of the discrete, and the reconciliation of the discrete, and the reconciliation of the discrete and the continuous. Everything flows. The epigraph is Heraclitus. This section explains how movement gets produced when action is treated as inference. Move a limb by predicting it is already moved. The generative model emits a proprioceptive prediction, the expected position, and the classical reflex enforces. The reflex enforces. Discharging that prediction error drags the muscle until the prediction comes true. Action is inference, run in the effector direction. There is no inverse model, no mapping from desired outcome back to motor command, because the command just is the prediction whose fulfillment the reflex enforces. Feldman's equilibrium point hypothesis falls out as the simplest case, a point attractor drawing the limb toward V. Promote position to velocity, and the same scheme becomes a spring obeying Hooke's law. The chapters move. Motor control is perception with the arrow reversed, one free energy descent doing both. This section explains how a continuous time system encodes its behavior. A continuous time creature stores the flow that generates its path, rather than the path itself. The flow is the function f, which gives each state its rate of change, and the system is drawn toward its attractor. Behavior then comes from prediction. You fix the vector field, integrate, and the path falls out. The section's two anchors are one move seen from two angles. Generalized Lotka. Volterra Dynamics manufacture an orderly sequence of peaks from predator-prey competition, the continuous shadow of Chapter 7's discrete plans. A Lorenz system manufactures chaotic itinerancy, orbiting one lobe before switching. The same primitive runs throughout. Encode how states change, and let integration produce what happens. This section explains generalized synchrony. Couple 2. Chaotic systems together and their joint trajectory collapses onto a lower dimensional synchronization manifold. They stop exploring the full product space and start tracking one another. Identical synchrony pins them to the line where x equals y, each one inferring the other's hidden state and copying it. Generalized synchrony relaxes this to any curved manifold, a reparametrization rather than a match. Frist pictures it as two songbirds learning to sing from the same hymn sheet. Here is the step that does the work. Let one system be internal states and let the other be the world. This coupling is inference, and inference is what representation actually names. A brain locks its dynamics onto the environments. Autism reads as the failure of that locking. This section explains how a hybrid model stacks a discrete decision process on top of a continuous movement process. Decision and movement are the same inference at 2 time grains, so you stack them. A discrete palm DP sits on top, selecting, at each tick, which segment of a continuous trajectory to enact below. The join is one primitive. Each discrete outcome names a point, a prior mean in continuous cause. Space and the continuous data flowing back scores that outcome's evidence. Bayesian model averaging descends, model evidence ascends. The interface runs both ways. Structurally, this is a Gaussian mixture. Assign continuous data to a categorical cluster, recast as inference. The delay period saccade anchors it. Choose one of 4 locations, then foveate its coordinates. Decisions become movements, and the movement sharpens the decision. This section summarizes the chapter's central claim about how movement works. To move is to hold a false belief and let the body make it true. That is the whole chapter compressed. In continuous time, free energy minimization needs no inverse model, no controller computing commands from goals. The agent predicts its limb already at the target, and reflex arcs discharge that prediction error by moving the limb there. The prediction is the command. Action exists only to null the discrepancy. Everything else, the Lotka-Volterra sequencing, the Lorenz-driven birdsong, 2 brains synchronizing onto a shared manifold, is the same move dressed in richer dynamics. The chapter closes by welding this continuous machinery onto the discrete POM-DP world of Chapter 7. Decisions become movements, and the sensory return carries them back to decisions. This part explains how model-based data analysis turns the brain's own inference machinery back on the scientist studying it. Every prior chapter assumed the brain inverts a generative model. This one turns that same machinery on the experimenter. You build an objective model of how a subject's subjective model produces behavior. Then you invert your model on their observed choices to recover their priors. This is inference about an inference, the same Bayes performed twice. Here is the generative primitive. Whenever a theory says a system infers, the scientist studying it becomes a second inferer of the same kind, and fitting the model is just running the theory's own inversion 1 level up. What you recover is a computational phenotype, the belief someone would need to hold for their behavior to be optimal. Pathology then reads as aberrant priors. The inference machinery works as it should, but it runs on distorted beliefs. This section explains the reflexive turn the chapter takes. The same inference the book has spent 9 chapters attributing to the brain, the scientist now runs 1 level up. The subject inverts a model of the world in order to act. The experimenter inverts a model of that subject's model, recovering the priors the subject must hold for its behavior to be. Bayes optimal. This is meta. Bayesian inference, the operator applied to itself. The subject's generative model becomes the likelihood term inside the scientists. This move converts active inference from a theory of mind into an instrument for measuring one. Its name is computational phenotyping. Obama's hammer guards the flank here. Active inference stays a tool with a bounded domain, useful within its reach, and not a universal solvent. This section explains how the theory turns its own method back on itself. Every prior chapter assumed the brain inverts a generative model to infer its world. This chapter aims that same machinery at the brain. The scientist builds an objective model of how the subject's own subjective model produces behavior, then inverts that model to recover the priors. The subject's own subjective model produces behavior, then inverts that model to instaur expere. The result is inference about an inferential process. The observer models the observed as a fellow modeler. The primitive here is self-application. The tool becomes its own measuring instrument, one Bayesian loop nested inside another. Its yield is computational phenotyping, reading a mind's parameters off its actions. There is a boundary to what this delivers. It recovers the priors a mind holds and stops short of the mechanism that runs them. A phenotype names which beliefs would explain the behavior. Whether those beliefs actually run inside the subject stays an open question. This section explains the meta-Bayesian methods, and the core idea is to apply Bayes to a Bayesian. The brain inverts a model of the world in order to act. The scientist then inverts a model of that inversion to recover the priors the brain must hold. The move that does the work is nesting. The subject's generative model sits inside the experimenter's likelihood function. To score how probable a parameter value is, you plug it into the subject's model, run active inference forward, and read off the predicted behavior. This is figure 9.1, the inner box sitting within the outer. One recursion yields two payoffs, each a side of Bayes' theorem. Estimating a subject's parameters gives you the posterior, and this is computational phenotyping. Adjudicating rival models gives you the evidence, and this is model comparison. Same machinery, lifted one meta level. Inference about inferers. This section explains how the same free energy machinery that generated behavior can be run in reverse to recover a subject's model. Every chapter until now ran the generative model forward. Fix the parameters, theta, minimize free energy, and watch behavior fall out. Section 9.3 turns the same crank backward. Take a real subject's action sequence as the data and minimize free energy over theta itself, recovering the model that would have produced it. The scheme is variational Laplace. It is the same predictive coding gradient descent, freed from the Gaussian likelihood assumption, approximating the parameter posterior as a bump around its most probable value. The move that carries the chapter is this. Fitting and inference are one operation at two levels. The free energy principle eats its own generative model as data. Solve the POM dp under theta, score the observed actions, and ascend the gradient. This part explains parametric empirical Bayes, which is Bayes applied to its own output. Variational. Laplace hands you, for each subject, a posterior over that subject's generative model parameters, one computational phenotype apiece. Parametric empirical Bayes treats those individual estimates as data generated by a second model, a general linear model in which theta equals x beta plus omega. Here, the columns of x are between subject covariates, age, drug, patient versus control, and beta holds their effect sizes. So the same inference machinery runs one level up. The empirical prior on each subject's parameters is now estimated from the whole cohort rather than fixed. And asking whether age shifts preference precision becomes model comparison over whether a beta element may leave zero, answered without reinverting anyone, by way of Bayesian model reduction. The recursion is the point. An inference's posterior is the next inference's observation. This section explains how to fit a Bayesian model to a brain's own Bayesian inference so that the prior beliefs it holds can be recovered from behavior. The move is this. To recover the prior beliefs the brain holds, you fit your model of its model. This is inference about an inferential process, one Bayesian level stacked on another. The recipe has 6 steps. First, collect the subject's choices. Second, write the subject's POM dp as a parameterized function. Third, turn that into a likelihood. Fourth, set priors. Fifth, invert by variational Laplace. Sixth, do group-level PEB. All 6 steps hang on one non-obvious primitive. The primitive is that the likelihood here is a simulator you score against, a forward run rather than a closed form. You run the agent's generative model forward under candidate parameters, ask how probable its actual choices were, and ascend the parameters that make the observed behavior most nearly fitting the priors that would rationalize what a subject did is itself the computational phenotype. This section explains how a single inversion procedure serves 2 very different experiments in generative modeling. The core idea is 2 experiments, 1 machine. The same 6-step inversion, building the subject's generative model, scoring the likelihood of her actions, then inverting to recover her precision parameters, runs identically whether that model is continuous or discrete. The substrate is a free variable that the scientific question fixes downstream, never the other way round. Adams and colleagues read smooth pursuit through a continuous model and correlate the recovered precision against MEG synaptic gain. Mirza and colleagues cast saccadic foraging as a discrete POM-DP and test whether epistemic value drives the search. Sinusoid, tracking versus seeing, categorization, differential equations versus Markov states, all of this is scenery. What stays invariant is the meta-Bayesian move, fitting an objective model of another agent's subjective one. This section explains how the whole family of psychiatric disorders falls out of a single move. Pathology is an intact inference engine running a corrupted prior. The machinery computing posteriors works normally, but the generative model carries aberrant beliefs. That one move generates the entire taxonomy. Almost always the corruption lives in a single dial, the precision balance between prior and likelihood. Tip it toward likelihood and spurious sense. Data overwrites belief, which is hallucination. Tip it toward prior, and a posterior stays fixed with no evidence to support it, which is delusion. Because the fault is a parameter rather than a defect, you can invert the behavior to recover the aberrant prior. Psychiatry becomes measurement. Predict any new disorder by asking which precision was mistuned and where. This section explains the summary move of Chapter 9.8. The same variational machinery, the book grants the brain, turned back on the brain, that is the whole move. A scientist builds an objective generative model of how a subject's subjective model produces behavior. The scientist then inverts it on observed choices to recover the priors and precisions the subject would have to hold for their behavior to count as Bayes optimal. Inference about an inferer. The yield is computational phenotyping. What a person believes becomes a measurable parameter, and pathology resolves as aberrant priors sitting inside intact machinery. Delusion is simply a posterior too precise for its evidence. Behavior turns into a non-invasive probe of the generative model, driving it across health and disease. This section explains how a single quantity, variational free energy, unifies the faculties the cognitive sciences once treated as separate. Start from one scalar, variational free energy, abound on surprise. Every faculty the cognitive sciences had carved into separate modules falls out as a special case of minimizing it. Perception is inference on a generative model. Action is that same inference run on proprioceptive predictions. Decision, attention, emotion, and homeostasis are the one imperative read-through dictions. The chapter's compression is Dennett's whole iguana, modeled the complete creature, coupled to its niche rather than subsystems with arbitrary boundaries. So the Bayesian brain, ideomotor theory, cybernetics, optimal control, and reinforcement learning stop being rivals. Each one is a projection of a single least action principle onto one domain. Unification here means the modules were never fundamental. Only the gradient was. This section explains how one principle, read backwards, becomes the whole of psychology. The usual move assembles a mind from perception, attention, memory, emotion, and decision as separate modules, the Jamesian categories every textbook inherits. This chapter does the opposite. It starts from a single imperative, variational, free energy minimization, hands a complete creature, a niche to survive in, and then derives the functions as facets of that one, solution. Dennett called this the whole iguana. Do not model the parts, model the animal, and let the parts fall out. The inversion that carries the chapter is that these functions may be arbitrary carvings rather than distinct processes. The brain rungs. They are how a generative model narrates its own self-evidencing. Perception, action, and planning are one thing seen from different angles. This section introduces the single move that organizes the whole chapter. One principle, minimize variational free energy, is claimed to close the adaptive problem entirely, and every cognitive faculty falls out as a reading of that single solution rather than a part bolted on. That is the chapter's whole move. Perception, action, selection, attention, and emotion are not primitives you assemble into a mind. They are projections of one minimization sliced by us after the fact. The inversion is what carries the weight here. Traditional psychology begins with the faculties and hopes they compose. Active inference begins with the complete creature in niche and derives the faculties. This lets phenomena studied in separate literatures, cybernetics, optimal control, and reinforcement learning reveal themselves as the same object seen from different learning, reveal themselves as the same object seen from different angles. This section recaps the whole argument, and what it exposes is a single fixed point approached from two independent directions. The low road starts mechanistically. A brain is a generative model. Perception is its Bayesian inversion, and since exact inversion is intractable, the objective becomes variational, free energy. The high road starts thermodynamically. A thing with a Markov blanket stays itself by avoiding surprising states, that is, self-evidencing, which is approximately the same minimization. Two premises that share nothing. Prediction error engineering on one side and statistical physics persistence on the other collapse onto one quantity. Perception and action stop being separate faculties. Both just minimize that discrepancy, one by changing the mind, one by changing the world. The convergence is the argument. A construct reachable from disjoint starting points is forced by that very convergence, not merely stipulated. This section explains how perception, action, selection, and emotion collapse into a single imperative. They look like separate faculties only until you derive them from one move, minimizing variational free energy under a single generative model. Read that one imperative 3 ways, and the 3 faculties appear. The integrative claim is reductive by derivation, not additive. You do not stack a theory of each construct. You show that each one is the same. Self-evidencing gradient projected onto a different variable. Belief updating, policy scoring, precision weighting. The chapter earns its title. Active inference as a unified theory precisely here. The dots were never independent. The predictive test of understanding is generative. Given the single principle, you can now reconstruct where any familiar psychological construct falls, rather than memorizing a list of them. This section explains how active inference reverses the ordinary story of the brain. Start by flipping the arrow. The old picture, which Hurley called the sandwich model, runs a stimulus forward through a cognitive filling to a response. Stimulus forward through a cognitive filling to a response. Active inference reverses the primary direction. Prediction descends from a generative model, and sensation is met only to be checked against what was already expected. What flows upward is the residual, the mismatch between prediction and data. A brain built this way has just two moves, and both are self-evidencing. It can compare predictions to data and revise, which is perception and learning. Or it can enact predictions to harvest the data it wants, which is action. These two moves are split by two imperatives. The epistemic imperative is to resolve uncertainty. The pragmatic imperative is to secure preferred outcomes. Predictive processing is this same insight loosened into a philosophy. Active inference is its constrained, formal core. This section places active inference inside the wider family it belongs to. The whole claim is simple. Prediction is the brain's primitive verb, and active inference is one constrained specialization of that idea. Predictive processing is the genus. It is the philosophical wager that brains are prediction machines, unifying perception, action, learning, and psychopathology under a single move, and reaching from sensory motor loops all the way up to social and cultural constructs. Active inference is a species inside that genus. It is the one that commits to specific machinery, generative models, free energy, precision, and Markov blankets. Predictive processing stays looser. It will also admit coupled inverse and forward models that active inference refuses. Here is the surprise that Parr and Pezzulo underplay. The very prediction, centrality that unifies everything is exactly what leaves predictive processing open to being read as internalist, as embodied, or as an activist. The genus underdetermines its own metaphysics. This section explains how perception works as inference and why it falls out of the same principle that drives action. Perception runs a generative model backwards. You never read the world off your senses. You hold a model of how hidden states generate observations, and Bayes' rule inverts it. The percept is the cause your model must posit to have produced this input. This is Helmholtz's analysis by synthesis. Resurfacing active inference's move is subsumptive. It stops treating this as a standalone Bayesian brain postulate and derives it from one imperative: minimize variational free energy. The same gradient that infers a cause also drives action, so perception and action fall out of a single principle rather than two. The generative primitive to carry is this. Any faculty here is what minimizing free energy looks like under a different partition of the model. This section explains the Bayesian brain hypothesis at the structural level. Perception is Bayesian inference. The brain infers the hidden causes of its sensations by inverting a generative model of those sensations. The surprise is that this names less a theory than a loose confederation. Each member commits at a different MAR level: Bayes' optimal multisensory integration, sampling algorithms, probabilistic population codes. These members are often mutually incompatible, and each one requires a separate Bayesian decision theory bolted on before it can reach action. Active inference's move is subsumption. It derives the whole family from a single imperative, minimizing variational free energy. Once that imperative is in place, action follows for free, because sampling the world to test a hypothesis is just that same minimization carried into the motor domain. Where the Bayesian brain had a scattered pluralism, active inference offers one generative principle. An object is what it does, and here the doing is singular. This section explains action control as the mirror image of perception. Action is perception, run backward. The same predictive coding machinery that infers the world's causes from exteroceptive input also drives movement from proprioceptive prediction. Believing that my hand grasps the cup precisely enough makes the hand move to fulfill the belief. There is no motor command, no inverse model, no cost function. The descending prediction is discharged by a peripheral reflex that cancels the proprioceptive prediction error. The one lever is precision. Action initiates only when the prior outweighs sensory evidence, which demands transiently attenuating sensory input so the belief wins rather than gets revised. Every rival framing becomes a special case of this single move: ideomotor theory, cybernetic set points, and optimal control's inverse models. Control is inference, completing itself. This section explains ideomotor theory as a structural primitive. Action is not commanded, it is predicted into being. Ideomotor theory has one move, the same action effect link read in two directions. Read forward, it forecasts what a movement will feel like. Read backward, it selects the movement whose forecast is what you want. Control is the inverse read of a forward map. Active inference inherits exactly this. A grasp is caused by the proprioceptive prediction that my hand holds the cup, and the body closes the gap to make that prediction true. The section's work is placement. William James's ideo plus motor is the historical name for the inversion that active inference formalizes, now with precision, weighting and sensory attenuation added as the machinery James lacked. This section explains cybernetics as the ancestor of action. Action is the old cybernetic loop wearing new mathematics. Behavior is selected by the discrepancy between a preferred state and the current one, and it acts to close the gap. This is tote, test, operate, test, exit, not stimulus and response. The sharp inheritance is Parr's perceptual control theory. What a system holds stable is a perception, never a motor output. Driving, you defend the speedometer, reading 90 miles per hour, while the actions serving it accelerate and brake, stay fluid and disturbance dependent. This is James's stable goals through flexible means. Control descends a hierarchy as set points. Higher levels name what and leave lower levels the how. Active inference is this same loop with a generative model bolted on. The one thing pure feedback lacked. It can anticipate the disturbance rather than only correct it after the fact. This section explains how active inference reframes optimal control theory. Optimal control computes the motor command. An inverse model inverts a cost function to select the action that reaches the goal. Active inference deletes that computation. The motor cortex emits a prediction, not a command, and action is whatever cancels the resulting proprioceptive prediction error. The inverse model collapses to a spinal reflex. The forward or generative model does the heavy lifting. The structural move is absorption. The controller dissolves into the model, cost becomes prior preference, and command becomes prediction. What was a separate optimizer minimizing value becomes inference. realizing a predicted trajectory. The brain does not solve control. It predicts and lets error do the moving. This section explains how active inference dissolves decision-making into inference. Fold value into belief, and choosing stops being optimization. Every other framework here, optimal control, reinforcement learning, Bayesian decision theory, keeps two ledgers. One is a probability of outcomes. The other is a separate utility over them. Each then maximizes their product by way of value functions and the Bellman recursion. Active inference collapses the second ledger into the first. A preference becomes just a prior over what you expect to observe. So the generative model runs optimistic, and finding the best plan becomes inferring the control sequence that makes the preferred future likely. The complete class theorems guarantee the move is always available. Any utility rewrites as a prior. Reward, discounting, and value functions dissolve. What survives is expected, free energy, the closest analog. This section explains how Bayesian decision theory splits a choice in two, and why that split turns out to be an illusion. Bayesian decision theory factors choice into two pieces. First, a probability, how likely each outcome is under a plan. Second, a separate utility scoring those outcomes. Action selection multiplies the two. The real work of the section is dissolving the seam between them. The complete class theorems, due to Wald, prove that for any decision and cost pair there exists a prior that renders it Bayes optimal. Probability and utility are therefore dual. Their separation is a degeneracy, a gauge freedom dressed up as structure. Active inference exploits exactly this. It absorbs utility into the prior, so that preference becomes a belief that preferred outcomes will occur. The generative model turns optimistic. The apparent divide between is and ought collapses into a single inference. This section explains how reinforcement learning and active inference diverge on the same underlying problem. Reinforcement learning and active inference attack the same Markov decision problems, but they ask different questions. Reinforcement learning asks which policy maximizes cumulative reward, and it answers with value functions and Bellman optimality. That answer comes in three flavors: learned directly from experience, which is model-free, learned from a simulated task model, which is model-based, or obtained by tuning policy parameters against reward, which is policy gradient. Active inference dispenses with reward, value, and Bellman entirely. A policy stops being a learned stimulus response map and becomes a hidden variable to be inferred, scored by expected free energy. The whole reward scaffolding evaporates because the problem is recast as inference rather than optimization. Here is how to predict the boundary. Wherever reinforcement learning invokes reward, active inference substitutes a prior belief about preferred outcomes. Same behavior, different master. This section explains planning as inference, the primitive that recasts control as a sane inverse problem. Perception already solves. Control stops being optimization the moment you notice it is the same inverse problem as perception. Perception infers hidden causes from observations. Planning as inference infers hidden actions from a desired observation. You clamp the future you want as if it were already seen, then read off the action sequence most likely to have produced it. The generative model runs backwards. The question it answers is not which policy maximizes reward. The question is, given that this outcome is true, what must I have done? Under this framing reward, value functions and Bellman optimality all dissolve. There is only one machinery, Bayesian inversion, pointed once at the past, meaning states, and once at the future, meaning controls. The agent plans by imagining the goal accomplished and inferring its own agency. This section explains how behavior and bounded rationality both fall out of a single quantity, read 3 ways. One functional, read 3 ways, is the entire move. Behavior minimizes free energy, and that single quantity decomposes into 3 terms. The first is deliberative, the expected free energy, which reaches preferred outcomes and resolves uncertainty. The second is perseverative, the variational free energy, which keeps gathering evidence for the action you already believe you are taking. The third is habitual, the prior over policies. There is no two-system architecture here, and no rational versus intuitive split in the manner of Kahneman. The mixture itself is inferred, weighted by context and by available compute. Bounded rationality then falls straight out, sharpening a belief before choosing costs, entropy, and that cost is already the complexity term, sitting inside free energy. The bound is endogenous. Accuracy against complexity is the objective, never a constraint stapled on from outside. This section explains the free energy theory of bounded rationality. Rationality is bounded by a price on precision, sharpening a belief before choosing costs. Entropy reduction, so the agent that minimizes free energy already computes the optimum trade-off between accuracy and complexity. Accuracy is the energy term, the expected value of the choice. Complexity is the energy term, the deliberation spent, making beliefs precise. The same 2 terms that split variational free energy and perception reappear here as the ledger of decision. Bounded rationality is what free energy minimization does when computation is not free. It is the same minimization now paying for the cost of thinking. Classical utility maximization keeps only the accuracy term. The second term is the whole surprise, an optimality that already carries the cost of thinking inside it. This section explains where feeling comes from in active inference. Feeling reads the slope of free energy. It tracks the rate of change, not the level itself. Active inference makes one move here. Affect reads the derivatives of free energy, never its level. You no longer need to know your surprise, only how it changes. Valence is the first derivative, free energy's rate of change over time. Falling free energy feels good, and rising free energy feels bad. This identification comes from Joffoli and Corricelli. Confidence and motivation ride the second derivative, which is precision, the curvature of the free energy landscape. Precision is inversely related to ambiguity. The precision of policy beliefs is the surrogate for expected dissent, and dopamine is its signal. One scalar, differentiated once and twice, generates the whole triad. Everything richer, like relief and disappointment, is just a higher derivative of the same quantity. This section explains how the same predictive machinery that models the world, turned inward, produces physiology as perception. Point the same inference engine inward, and physiology becomes perception. A creature's generative model predicts not only the world, but its own interior. Priors over interoceptive observations are the viable ranges of body temperature and blood sugar. Homeostasis then falls out as prediction. Error, correction. A surprisingly high temperature is error, and an autonomic reflex like vasodilation is the interoceptive twin of a motor reflex steering proprioceptive error. Allostasis is that loop deepened, finding shade before overheating, raising cardiac output before the run, shifting the set point in anticipation. From reflex to goal-directed, the whole regulatory nest is one machinery aimed at the body rather than the limbs. Affect is that machinery read from inside, how good or bad each event is for staying alive. This section explains attention and salience as two quantities inside Friston's active inference model. A term becomes definable the moment you stop asking what it means and ask which quantity in the model it is. Attention is the precision the agent assigns to a sensory channel. It is gain control over data already in hand, an attribute of beliefs. Salience is the expected information gain of a policy. It is an attribute of actions, the anticipated value of data not yet collected. One axis, two positions, reading what you measured versus designing the next measurement. Friston's anchor is the scientific experiment. Attention weights your best existing data toward the hypothesis. Salience chooses the experiment that will yield the sharpest data next. They conflate because maximally precise data is both worth attending and worth seeking. The formalism dissolves a century of psychological ambiguity by refusing the word and naming the term. This section explains how one-shot generalization arises from finding the cause behind the data and why counting correlations never reaches it. The first idea is that recovering the cause is what lets you generalize from a single example. Correlation counting cannot get there. Hold the traffic intersection in mind as the anchor. A naive observer logs endless co-occurrences. A red car stops, a tall man crosses. But it stays trapped in mechanism. Blindness, taking the stopping of cars to explain the walking of pedestrians. This is the same error that cannot tell whether rain explains wet grass, or wet grass explains wet grass, or wet grass explains the rain, the confusion Parr made central. Now, infer the hidden rule of the traffic light. That single latent cause collapses all of it into one. It predicts better, it discards every sensory detail, so the color of the car becomes irrelevant, and because of that, it transfers to a different city. Active inference builds this in as structure learning. Recover the deep generative model of the latent rule, and few-shot generalization together with learning to learn fall out on their own. This section closes the book by showing that active inference does not stop at the single organism. One functional, minimized, generated the whole book. And here is where Parr, Pezzulo, and Friston push that same generator outward. Copy the agent and let the copies couple. Mutual prediction, turn-taking, morphogenesis. The drift is from a science of individuals to a science of societies. Now swap the process theory for connectionist gradients and the same object surfaces under a second name. The variational autoencoder's evidence lower bound is exactly variational free energy. So, social dynamics and machine learning are that one principle read at a new scale and on a new substrate. The directions stay open because the generator already subsumes them. This section explains how a theory of a single mind becomes a theory of society with nothing added. Nothing new is added to make a society. That is the whole claim. The same agent that minimizes free energy over its own sensory boundary becomes a social science the moment you instantiate it twice in a shared world. Each agent is part of the other's environment, so each predicts the other. Coordination, turn-taking, morphogenesis, and resistance to dispersion all fall out as the fixed point of mutual prediction. Society reuses the very mechanism of cognition, composing it with itself, agent into agent. The same machinery suffices, replicated, with no extra layer bolted on top. The generative move is this. Whenever a theory defines one unit by what it does to its niche, replicate the unit and let each one be the other's niche. Emergence is the equilibrium of that recursion, and mind spills past the skull. This section explains how machine learning and active inference are the same objective, read in two directions. Machine learning spends the variational bound inward, fitting a connectionist generative model to data. Active inference spends the identical bound outward, selecting action. The bridge is an identity rather than an analogy. The variational autoencoder's evidence, lower bound, is variational autoencoder's evidence, lower bound is variational free energy itself, accuracy minus complexity, with the complexity bound overfitting. So the whole machine learning menagerie is already this book's inference engine, missing only the action loop. The Helmholtz machine, the stacked Boltzmann machines, the VAE, the GAN's race between generator and discriminator, each is that same engine. The primitive to carry is this. Once perception is bound, minimization, scaling perception through deep nets and scaling control become one problem, differing only in which variable you hold fixed. This section summarizes the chapter's single principle and what it asks of you. One principle: minimize surprise about your own sensations, regenerates perception, action, choice, and feeling. It reveals all four as facets of a single inference, where a naive view would treat them as four separate faculties stitched together. The chapter's closing: move is the sharp one. The principle exists only in the running of it. You can hold it in mind, but that is never enough, because it is the kind of thing that lives in being enacted. You are already an instance of it. The saccade that resolves a blurred shake, the hand that lowers the shower's heat toward your model of comfort, these are active inference in execution. They do not illustrate the theory. They are the theory running. The Tolkien epigraph does structural work. The book ends on a path rather than a result, offering a way to walk rather than a conclusion to accept, because a generative principle earns assent through enactment and not through argument. The reader was never the audience. From the first page, you were a worked example of the very theory being summarized here.